Hey everyone! In this video, we're going to learn about one-dimensional projectile motion. We'll start with a quick overview. Then, we'll look at three different examples. Example 1 is a ball dropped from rest. Example 2 is a ball that starts with a downwards velocity. And example 3 is a ball that starts with an upwards velocity. For each example, we'll start by walking through a few practice questions. Then we'll explore each scenario and find the height and velocity at different time points. And then we'll talk about the motion graphs. After that, we'll compare all three examples to get a better idea of how 1D projectile motion works. And at the end, we'll do a summary of the main points. Let's start with a quick overview of one-dimensional projectile motion. We covered the basics of projectile motion in the last video, so make sure you watch that first. In 1D projectile motion, an object only moves in the vertical direction, or the y direction, and the horizontal velocity is 0. In 2D projectile motion, an object does have some horizontal velocity, so it moves in the vertical and horizontal directions, and we use the x and y kinematic equations. This video will focus on 1D projectile motion. There's only three ways this motion can start. The object is dropped from rest with 0 initial velocity, it has an initial downwards velocity, or it has an initial upwards velocity. 2D projectile motion uses x and y kinematic equations, but 1D projectile motion only uses the y equations for vertical motion. The acceleration will always be 9.8 meters per second squared downwards, which is g, the acceleration due to gravity. If we choose up to be the positive direction, then we're going to plug in negative g, or negative 9.8 meters per second squared, for the acceleration ay, because it accelerates in the negative direction. If an object starts with an upwards velocity, so it moves up and then falls down, the vertical velocity, vy, is 0 when the object is at its maximum height. That's a value we might need to plug into our equations at that point. So that's a quick overview. 1D projectile motion is really just a specific case of 1D motion in the y direction, where the acceleration is 9.8 meters per second squared downwards. But we'll explore these examples in a lot more detail, so we have some intuition about projectile motion. Let's start with the simplest example of 1D projectile motion, an object dropped from rest. A ball is dropped from rest from a height of 30.6 meters. How long does it take the ball to hit the ground? And what is the ball's speed when it hits the ground? First, let's pick out the important information. The ball is dropped from a height of 30.6 meters. The ball is dropped from rest, which means the initial velocity is 0. We want to find the time and the final speed, or the magnitude of the final velocity, when the ball hits the ground. Next, we always need to choose which directions are positive and negative. We could say up is the positive y direction, or down is the positive y direction. If up is positive, the initial y position would be 30.6 meters, and the final y position at the ground would be 0 meters. If down is positive, then the initial y position is 0 meters, and the final y position is 30.6 meters. Since this is projectile motion, the acceleration is 9.8 meters per second squared downwards. If up is positive, then the acceleration, ay, is negative. The ball would accelerate in the negative direction and the y value would decrease over time. If down is positive, the acceleration would be positive. The ball would accelerate in the positive direction and the y value would increase over time. You can set up your axis either way. Just make sure you stay consistent with your directions and the positive and negative signs. In this course, we're usually going to say up is the positive y direction. When we study projectile motion, we're usually describing the motion of a point at the center of the object, technically the center of mass. When we draw a picture, the object has some width and height, but we're going to describe the position of the center of the ball. So the ball hits the ground when its center has a y position of 0. Also, when a question wants us to find a value when the object hits the ground, it's asking about the instant it hits the ground, or we can think of it as the instant before it hits the ground. If we're trying to find the speed at that point, we're not going to say the ball stops when it hits the ground and the final speed is 0. The question is focusing on the projectile motion of the ball. So we're looking for the time and speed when the ball has the same y position as the ground, which in this case is 0 meters. So don't think about the physical interaction with the ground, just focus on the projectile motion of the ball. Alright, so first, how long does it take the ball to hit the ground? The ball starts with 0 velocity, then it accelerates downwards, and we want to find the time when the y position is 0. Which equation can we use for that? The first equation for displacement doesn't involve time. The second equation only applies if there's no acceleration and the velocity is constant, or it can tell us the average velocity. We're not really going to use this equation in the y direction. The third equation for acceleration does apply, but we would need to know the final velocity to find the time. The fourth equation relates the initial and final y positions, the initial velocity, time, and the acceleration. We can use this equation because it has the variable we're trying to find, t, and we have values that we can plug in for everything else. The fifth equation relates the initial and final velocities, the acceleration, and the initial and final positions, but it doesn't include time. So let's use this equation. We plug in 0 meters for the final position when the ball hits the ground, 30.6 meters for the initial position, 0 meters per second for the initial velocity, and negative 9.8 meters per second squared for the acceleration. If we simplify that and we drop the units, we end up with this. We can add 4.9 t squared to both sides, divide both sides by 4.9, and then take the square root of both sides to find t, which is 2.5 seconds. So after the ball is released, it takes 2.5 seconds to reach the ground. Next, what is the ball's speed when it hits the ground? Which equation can we use for this part? Now we have a value for the time it hits the ground. So we could use this equation and plug in the time, or we could use this equation and plug in the final position. Let's use this one first. Remember, this equation can also be written like this, if we replace delta Vy with Vy final minus Vy initial, and we rearrange the equation. Also, this uses delta t, but that's the same as just t, since the initial time point is 0 seconds. So we plug in 0 meters per second for the initial velocity, negative 9.8 meters per second squared for the acceleration, and 2.5 seconds for time. That gives us negative 24.5 meters per second for the final velocity. Speed is the magnitude, or the absolute value of the velocity, so the final speed of the ball would be positive 24.5 meters per second. Now let's try using the other equation. We plug in 0 meters per second for the initial velocity, negative 9.8 meters per second squared for the acceleration, 0 meters for the final position, and 30.6 meters for the initial position. We can simplify that, take the square root of both sides, and we get 24.5 meters per second for the final speed of the ball. If you want, you can keep the values and take the square root of that, so you don't have to round anything in the middle of the calculation. Notice how this equation will always give us a positive value for v, because it's squared in the equation. So it's going to give us speed, the absolute value of velocity. Alright, so those are the answers to this question. If any object is dropped from a height of 30.6 meters with no initial velocity, it will always take 2.5 seconds to hit the ground, with a speed of 24.5 meters per second. Questions like this are common, where we have to find some values at one point in the motion, usually when the object hits the ground. Now, to get a better idea of how this motion works, let's explore one-dimensional projectile motion using this scenario. So, a ball is dropped from rest with no initial velocity from a height of 30.6 meters. We're using a ball in this example, but everything we're going to see applies to any object. Since we're ignoring air resistance, all objects accelerate downwards at the same rate, so they all follow the same motion. What's happening to the y position of the ball over time? It starts at 30.6 meters and decreases as the ball falls. What's happening to the velocity? The ball starts with no velocity, and then it moves faster as it falls. Let's start by exploring the position over time. Here's a snapshot of the ball every half second. If we look at the spacing between each snapshot, the ball falls a greater distance during each interval of time. Why is that? The ball is in projectile motion, or free fall, so it's accelerating downwards because of gravity. It doesn't move very far in the beginning because the velocity starts at 0. As the ball speeds up, it moves a greater distance during each second, or each half second. Let's find the y position of the ball at each time. What equation can we use to do that? The displacement equation doesn't include time. The acceleration equation doesn't include the y position. This equation would work because it has the variable we're trying to find, and we know everything else. And this equation doesn't include time. So let's use this equation. As a side note, the subscripts f and I mean the final and initial positions. But you might see this equation written like this, where the initial position has the subscript 0, which means the position at time 0, and the final position doesn't have a subscript. These equations mean the same thing. We can plug in a value for time and get the y position. Usually, we're focused on 2 points in the motion, so we call the first one initial and the second one final. Final doesn't have to mean when the ball hits the ground, it's just the second point that we're focusing on. So when we find the y position at each time, you can think of each one as the final y position in the equation, but we're just going to label them as y. So what's the y position when t equals 0.5 seconds? We plug in 30.6 meters for the initial y position, 0 meters per second for the initial velocity, 0.5 seconds for the time, and negative 9.8 meters per second squared for the acceleration. That gives us 29.4 meters for the y position at 0.5 seconds. At 1 second, we plug in 1 second for t and the same values for everything else, and we get 25.7 meters for the y position at 1 second. At 1.5 seconds, the y position is 19.6 meters. At 2 seconds, it's 11 meters. And at 2.5 seconds, the y position is 0 meters, which happens to be the time when the ball hits the ground. Notice how the equation is giving us smaller values for y as time increases. The right side of the equation starts with 30.6 meters, the initial velocity is 0, and the acceleration is negative, so we're subtracting from the 30.6 meters as time increases. So now that we have these values, let's graph the y position versus time. The horizontal axis is time in seconds, which increases from left to right. The vertical axis is the y position in meters, and up is positive, so it happens to look like the physical y-axis over on the left. The first point on the graph would be when t is 0 seconds and y is 30.6 meters. The next point is when t is 0.5 seconds and y is 29.4 meters. Here's all the points we found. If we calculated the y position at smaller time intervals, we could plot more points. And if we watch the y position as the ball falls, here's what the graph looks like. First, keep in mind that this is a graph of one-dimensional motion. It's not showing us a two-dimensional path. The ball only moves down, it's not moving to the right. Next, if you're familiar with functions, this is a graph of this function, which is the kinematic equation we just used to find the y position. This notation means y as a function of t, or position as a function of time. Next, note that the curve, which is the term for the line that we graphed, is actually a curve. The position versus time graph is a curved line if the object is accelerating. Next, notice that the curve crosses the horizontal axis at 2.5 seconds, when the y position is 0 and the ball hits the ground. But the graph also extends beyond that point. This kinematic equation will give us negative y values after that time. If we plug in 3 seconds for t, the y position is negative 13.5 meters. In the real physical scenario, the ball stops when y equals 0. But if the ground wasn't there, the motion would continue and the ball would have negative y positions based on the axis we set up. So this is a reminder that when using kinematic equations, always check that the values you get actually make sense in the physical scenario that you're using them for. Finally, notice that the curve starts at the initial y position, 30.6 meters. If we changed the initial height that we dropped the ball, the entire curve would shift up and down without changing shape, and the x-intercept would move left and right. For example, if the ball was dropped from a lower height, the ball would hit the ground in less time. So that's what the ball's y position looks like during this motion. But what's happening with the velocity? Which equation can we use to find the velocity at each time point? Remember, this equation is for the average velocity, and it doesn't tell us the velocity at some time if there's acceleration. We could use the equation for acceleration by plugging in the initial velocity, the acceleration, and each time. We can't use this equation to find the final velocity. And now that we have y values at each time, we could use this equation. However, we'd be plugging in values for y that we calculated and rounded. So let's use this equation and plug in the exact time values. At 0.5 seconds, we plug in 0 meters per second for the initial velocity, negative 9.8 meters per second squared for the acceleration, and 0.5 seconds for the time. That gives us negative 4.9 meters per second for the velocity at 0.5 seconds. At 1 second, the velocity is negative 9.8. At 1.5 seconds, it's negative 14.7. At 2 seconds, it's negative 19.6. And at 2.5 seconds, it's negative 24.5. So that's the velocity of the ball at each time point. Here's what the ball's velocity vector would look like from 0 to 2 seconds. The velocities are negative because they point in the negative y direction. Notice how the magnitude of the velocity and the length of the vector increases as the ball falls. At 1 second, the velocity is negative 9.8, and at 2 seconds, it's twice that, negative 19.6. This is basically the definition of acceleration. The ball is accelerating at negative 9.8 meters per second squared, so the velocity changes by negative 9.8 meters per second every second. If we line up the velocity vectors at each second, we can see how they change over time. That change between each second is the acceleration. The velocity vector increases in magnitude, or length, by 9.8 meters per second every second. Next, what would the velocity graph look like? The horizontal axis is always time, and now the vertical axis is the y velocity in meters per second, with positive values going up and negative values going down. So the vertical axis is not the height, it's the velocity. Let's plot the values that we found. The velocities are negative, so they're below the horizontal axis. If we graph the full curve as the ball falls, it looks like this. This time, the graph is a straight line. The velocity starts at 0, and it has a negative slope. This is a graph of the kinematic equation we used to find the velocities, which is written here as velocity as a function of time. The y-intercept is 0, which is the initial velocity, and the slope of the velocity graph is the acceleration, the change in velocity over the change in time. After each second, the velocity decreases by 9.8 meters per second, or we could say it increases in the negative direction. And the velocity would keep increasing in the negative direction if the ground wasn't there to stop the motion. Finally, what would the acceleration graph look like? The horizontal axis is time, and the vertical axis is acceleration in meters per second squared. In this course, we're only going to deal with motion where the acceleration is constant. In projectile motion, the acceleration versus time graph looks like this. It's a constant negative 9.8 meters per second squared the entire time. It's negative because we chose up to be positive. Written out like this, acceleration as a function of time is just a constant value. The variable t doesn't appear on the right because acceleration does not depend on time. It's always the same value. Now let's look at the position, velocity, and acceleration graphs together. Keep in mind that the vertical axes represent different things and use different units. The y position starts at 30.6 meters and decreases over time as the ball falls. The ball hits the ground when y equals 0. The velocity starts at 0 meters per second because the ball is dropped from rest, and the velocity increases in the negative direction over time because it's speeding up in the negative y direction. And the acceleration is negative 9.8 meters per second squared the whole time. The slope of the velocity graph is the acceleration, the change in velocity over the change in time. The acceleration is constant, so the slope of the velocity graph is constant, which is why it's a straight line. The slope of the position graph is the velocity, the change in position over the change in time. The slope of the curve, or the slope of the line tangent to the curve, is the velocity at that time. At t equals 0 seconds, the slope of the position graph is 0, and the initial velocity is 0 meters per second. The slope at 2 seconds is negative 19.6, which is the velocity at 2 seconds. The velocity changes over time, so the slope of the position graph changes over time, which is why it's a curve. So that's what 1D projectile motion looks like given these initial conditions, where an object is dropped from rest at some initial height. Now let's look at the next example. We'll go through these a lot faster. The second example is an object with an initial downwards velocity. A ball starts at a height of 25.7 meters with a velocity of 9.8 meters per second downwards. How long is the ball in the air? And how fast is it moving when it hits the ground? So, the ball starts at an initial y position of 25.7 meters with an initial y velocity of negative 9.8 meters per second. We know the acceleration is negative 9.8 meters per second squared, which happens to be the same value as the initial velocity, but they're two different things. The question says, how long is the ball in the air? Which is another way of asking for the time when the ball hits the ground. Then it says, how fast is it moving when it hits the ground? This means we're looking for the final speed, which is the magnitude of the velocity. So to find the time when the ball hits the ground and the y position is 0, we'll use the same equation as the first example. We plug in 0 meters for the final position, 25.7 meters for the initial position, negative 9.8 meters per second for the initial velocity, and negative 9.8 meters per second squared for the acceleration. When we simplify that, we get this equation. This time, we can't rearrange this equation to isolate t. If you have a calculator with a solve feature, you can plug in this equation and ask it to solve for t. If we do that, we get two values for t, positive 1.5 seconds and negative 3.5 seconds. Since we're looking for a positive time value, a time later than 0 seconds, then the answer would be positive 1.5 seconds. We'll explain that more in a second. If we don't have a calculator that can solve this, we need to use the quadratic formula, which is covered in the basics section. First, we need to rearrange this equation so it's in this form. A, B, and C are the coefficients, and each term is added together. If we rearrange things in our equation, A is negative 4.9, B is negative 9.8, and C is positive 25.7. Now we can plug those values into the quadratic formula to solve for t. Remember, A is just a coefficient, the value being multiplied by t squared. It's not the acceleration. When we calculate this using the plus sign and the minus sign, we get two answers for t. So t equals negative 3.5 seconds, or positive 1.5 seconds. But how can we have two answers for the time when the ball hits the ground? And why is one negative? Let's look at a graph of the y position versus time. It starts at 25.7 meters, and the y position equals 0 at 1.5 seconds. But this graph, and the projectile motion of the ball, is described using this equation. This equation and the graph aren't restricted to positive time values. The graph keeps going in both directions. We're looking for the time when y equals 0, which happens at positive 1.5 seconds and negative 3.5 seconds. The kinematic equation doesn't know there's a ball hitting the ground. It's going to give us all of the values that satisfy the conditions we give it. So, as a rule of thumb, we're going to ignore negative time values and just use the positive value we get from the quadratic formula. But always double check that the values you get make sense in the physical scenario. In this case, the time when the ball hits the ground must be a positive time after 0 seconds. So the answer would be the positive 1.5 seconds. Alright, now let's find the speed of the ball when it hits the ground. We'll use the same equation that we used in the first example. We plug in negative 9.8 meters per second for the initial velocity, negative 9.8 meters per second squared for the acceleration, 0 meters for the final position when the ball hits the ground, and 25.7 meters for the initial position. If we simplify that a little and then take the square root of both sides, we get 24.5 meters per second for the final speed of the ball, which is what the question is asking for. Since the velocity is in the negative y direction, the final velocity would be negative 24.5 meters per second. So that's the time and the speed when the ball hits the ground. Now let's explore this motion in more detail. An object starts at a height of 25.7 meters with an initial velocity of 9.8 meters per second downwards. Here's what this motion looks like. And here's a snapshot of the ball at half-second intervals. Like the last example, the ball falls a greater distance during each time interval because it's accelerating. But this time, the ball starts with some velocity, so it moves further in the first interval compared to when it was dropped from rest. We can find the y position at each time point using the same equation as before. But this time, we have a value for the initial velocity. At 0.5 seconds, the y position is 19.6 meters. At 1 second, it's 11 meters. And at 1.5 seconds, it's 0 meters, which is when the ball hits the ground. Here's what the position versus time graph looks like for this motion. The y position starts at 25.7 meters, and it reaches 0 meters at 1.5 seconds when the ball hits the ground. It's harder to see, but this position graph is still a curved line because the ball is accelerating. Now let's find the velocity at each time point using this equation. We plug in negative 9.8 meters per second for the initial velocity, negative 9.8 meters per second squared for the acceleration, and we plug in each time value. Here's what the ball's velocity vector looks like at the first 3 time points. The ball starts with a negative velocity, and it accelerates downwards, so it speeds up and the length of the vector increases. Just like in the first example, the velocity at each second is the previous velocity plus the change in velocity due to the acceleration. It doesn't matter what the ball's initial velocity is, it always changes by negative 9.8 meters per second every second. And here's the velocity versus time graph for this motion. Now, the velocity starts at negative 9.8 meters per second, but the slope of the velocity graph is still the acceleration. Here's all 3 graphs for this motion. Remember, the slope of the position curve is the velocity. Since the ball starts with a negative velocity, the position curve starts with a negative slope. So that's what the projectile motion looks like for an object that starts at some height with an initial downwards velocity. Now let's look at one more example, an object with an initial upwards velocity. A ball is launched from the ground with a velocity of 24.5 meters per second upwards. What is the maximum height that the ball reaches? How long is the ball in the air? And what is the speed of the ball when it hits the ground? So this time, the ball starts at the ground with an upwards velocity. The question didn't explain how. We could imagine it was launched upwards and it started at ground level. But that's not important for projectile motion problems. We're just given the initial height and velocity. The ball starts out moving upwards, it reaches some maximum height, then it falls back down and hits the ground. So first, how do we find the maximum height of the ball? There is an important thing we need to remember about projectile motion. The vertical velocity, Vy, is 0 when the object is at its maximum height in the trajectory. At this point, the ball is reversing direction, so it's not moving up or down at that moment. With that information, we know the initial velocity, the velocity at the maximum height, and the acceleration. So which equation can we use to find the y position at the maximum height? The only one we can use with the information we have is this equation. For this part, we're treating the maximum height as the final position. So we plug in 0 meters per second for the final velocity, 24.5 meters per second for the initial velocity, negative 9.8 meters per second squared for the acceleration, and 0 meters for the initial position. We can simplify that and rearrange the equation to isolate the final position, and we get 30.6 meters, which is the y position of the ball at the maximum height, when the velocity is 0. We also could have rearranged the original equation, keeping everything as variables, and then plugged in the numbers. Next, we want to find how long the ball is in the air. So what's the final time when the ball comes back down and hits the ground? For this part, we can use the same equation that we used in the last examples. Now, we're going to say the final point is when the ball hits the ground. So we plug in 0 meters for the final position, 0 meters for the initial position, 24.5 meters per second for the initial velocity, and negative 9.8 meters per second squared for the acceleration. We can simplify this equation, and if we want, we can use the quadratic formula to solve for t. But if we assume that the value of t is not 0, then we can just divide everything by t. Then we can rearrange the equation, and we get 5 seconds for t, the time it takes the ball to reach the ground. Now let's answer the last part. What is the speed of the ball when it hits the ground? First, we'll solve this with the same equation that we used in the previous examples. We plug in 24.5 meters per second for the initial velocity, negative 9.8 meters per second squared for the acceleration, 0 meters for the final position, and 0 meters for the initial position. That gives us 24.5 meters per second for the final speed of the ball. But now that we know the final time when the ball hits the ground, we could also find the speed using this equation. We plug in 24.5 meters per second for the initial velocity, negative 9.8 meters per second squared for the acceleration, and 5 seconds for time. That gives us negative 24.5 meters per second for the final velocity, and the final speed is the absolute value of the velocity, so positive 24.5 meters per second. Notice that the final velocity is the same as the initial velocity, except the final velocity is negative. When an object in projectile motion has the same initial and final y position, it starts and ends at the same height, the trajectory is symmetric. The initial and final vertical velocities are the same, but in opposite directions. We'll explain this more in a minute, but this fact is something you'll be expected to know about projectile motion. So we could have just answered this part conceptually by knowing that the final speed is the same as the initial speed, because the ball starts and ends at the same height. Now let's take a closer look at this motion, where an object starts with an upwards velocity. Here's what the motion looks like. What's happening to the position over time? And what happens to the direction of the velocity? Here's snapshots of the position at half-second intervals. Since the ball is in 1D motion, its path on the way up overlaps the path on the way down. So let's split up the snapshots with the ball moving upwards on the left and falling back down on the right. Using the same equation as before, we can find the y position of the ball at each time point. And here's the position versus time graph for this motion. Again, this might look like a two-dimensional trajectory of an object moving through the air, but this is just a graph of the height over time. So the y position starts at 0 meters, then it increases as the ball moves upwards. The ball reaches a maximum height of 30.6 meters at 2.5 seconds. Then the y position decreases as the ball falls down, and it reaches 0 meters again at 5 seconds. Notice that the time at the maximum height is half of the total time. That's because this trajectory is symmetric. It takes 2.5 seconds to go up and 2.5 seconds to fall down. Also, notice that the y position is the same at equal times before and after the maximum height. Half a second before the maximum height, it's at 29.4 meters. And half a second after the maximum height, it's at 29.4 meters again on the way down. So that's the position. What's happening to the velocity? We can use the same equation as before to find the velocity at each time. Then we can graph the velocity. It starts out moving 24.5 meters per second upwards, which is positive. As the ball rises, it slows down because of gravity. So far, we've only seen objects falling down, but for the first half of this motion, the velocity is upwards and the acceleration is downwards. Gravity subtracts from the velocity each second, so the ball slows down. Eventually, the velocity reaches 0 when the ball is at the maximum height. After that point, the ball begins to fall down and the velocity reverses direction. On the way down, the acceleration acts in the same direction as the velocity, so it speeds up as it falls. The graph is a straight line that crosses the horizontal axis at one point. So if we're looking for the time when the ball is at the maximum height, we're just solving this equation for the time when the graph crosses the horizontal axis and the y velocity is 0. Now let's look at the velocity vectors. The velocity has the same magnitude when the ball is at the same height, but they're in opposite directions. If we line up the velocity vectors at each time point, we can see how they're changing. This sort of looks like the velocity versus time graph. It starts out pointing upwards. It decreases as the ball slows down. It's 0 at the maximum height. Then it reverses direction and increases as the ball falls. If we look at 1-second intervals, each velocity vector is the previous vector plus the acceleration. For example, the velocity vector at 0.5 seconds is 19.6 meters per second upwards. The change in velocity each second due to gravity is negative 9.8 meters per second. If we add these two vectors tip to tail, the resultant vector is 9.8 meters per second upwards, 19.6 minus 9.8. This is the velocity vector of the ball 1 second later. Again, the vector changes by negative 9.8 meters per second, so 1 second after that, the velocity is 0. We keep adding this downwards vector each second, so the velocity vector starts pointing down and gets longer. Here's all three graphs for this motion. The position starts at 0 meters, increases to its maximum height, then comes back down to 0 meters. The slope of the position graph is the velocity, so it starts with a positive slope, then the slope is 0 at the maximum height when the velocity is 0, then the slope is negative on the way down. This velocity graph is a good way to see how gravity is actually affecting the motion. The slope of the velocity graph is the acceleration, and the slope is the same when the velocity is positive or negative. Gravity isn't acting differently when the ball is moving up or moving down. It just changes the velocity by negative 9.8 meters per second every second, regardless of the direction. This creates an interesting position graph. The ball moves in one direction, stops, and then moves backwards. But the velocity just keeps changing the same amount every second. So that's what projectile motion looks like for an object that starts with an upwards velocity. Now, let's do a quick comparison of all three examples to get a full picture of one-dimensional projectile motion. You might have noticed some similarities with the ball's motion in each example. In example 1, the ball started at 30.6 meters with zero velocity. It hit the ground in 2.5 seconds with a velocity of negative 24.5 meters per second. In example 2, the ball started at 25.7 meters with a velocity of negative 9.8 meters per second. It hit the ground in 1.5 seconds with a velocity of negative 24.5 meters per second. In example 3, the ball started at 0 meters with a velocity of 24.5 meters per second upwards. It reached a maximum height of 30.6 meters in 2.5 seconds, and the velocity was 0 meters per second. Then it fell down, and 2.5 seconds later, it hit the ground with a velocity of negative 24.5 meters per second. All of these motions have different starting points, different initial values, but in a way, they're all segments of the same trajectory. The motion in example 1 is the second half of the motion in example 3. If we started the clock 2.5 seconds later, and the ball started at the maximum height, we get the motion in example 1. It starts at 30.6 meters with zero velocity. The motion in example 2 starts 3.5 seconds later than example 3. It also starts 1 second later than example 1. Example 2 starts at 25.7 meters when the ball is already falling down at negative 9.8 meters per second. Here's the position and the velocity of the ball at each time point for example 3. Example 1 starts at 2.5 seconds, or halfway through example 3. And example 2 starts at 3.5 seconds, or 1 second after the maximum height. We can also look at the graphs. Here's the position and velocity graphs for example 3. If we shift the curves 2.5 seconds to the left, we get the graphs for example 1. We're basically starting the clock 2.5 seconds later in the motion when the ball is at the maximum height with zero velocity. And if we shift the curves 3.5 seconds to the left, we get the graphs for example 2. The ball starts at a lower height on its way down, and it starts with a negative velocity. So that's what one-dimensional projectile motion looks like using 3 different examples. That's everything we're going to cover in this video. Let's do a summary of what we need to know. In one-dimensional projectile motion, an object only moves in the y direction, or the vertical direction. The object could be dropped from rest with no velocity. It could start with a downwards velocity, or an upwards velocity. These are the kinematic equations for motion in the y direction, but we don't really use the equation for average velocity. The acceleration will always be 9.8 meters per second squared downwards. If we choose up as the positive direction, then we plug in negative 9.8 meters per second squared for AY. The equations that we use in different problems will depend on the information we have and what we're trying to find. We can use this equation to find the y position, or the height, at a certain time. We can use this equation to find the velocity at a certain time, or this equation to find the velocity at a certain height. We can use this equation to find the time when the object is at some height, like the time when it hits the ground and the motion stops. We might have to use a calculator to automatically solve for t, or we can use the quadratic formula. Remember that the y position versus time graph is a parabola, so there's two different times when the object is at a certain height. If one time is positive and one is negative, we're probably looking for the positive time. But when using any kinematic equation, always check that the values you get make sense in the physical scenario. If an object moves up and then down during its motion, the y velocity is 0 at the maximum height. And we can use that value and this equation to find the maximum height. If the initial and final heights are the same, the trajectory is symmetric. This means that the final y velocity is the same as the initial y velocity, but it has the opposite sign. This also means that the time it takes to reach the maximum height is half of the total time. Even if the trajectory is not symmetric, the object will be at the same height at equal times before and after the maximum height. It also has the same velocity at the same height, but in opposite directions. This applies to all motion graphs, not just projectile motion, but the slope at a point on the position graph is the velocity at that time, and the slope at a point on the velocity graph is the acceleration. The acceleration in projectile motion is always 9.8 meters per second squared downwards, which in this case is negative. So the slope of the velocity graph is constant, and it's a straight line. The velocity changes, so the slope of the position graph changes, which makes it a curved line. So that's it for this video. Thanks for watching, and I'll see you in the next video on projectile motion in 2 dimensions.